All right, so today we are looking at logarithmic functions. So these go with exponentials. We kind of have them hand in hand because our parent graph for logarithmic is f of x equals log base b of x. It's really important that you know how to say that intelligently. So when we read a logarithm, log base b of x is how we would read that. And our parent function is the inverse of y equals b to the x, which would be an exponential. So exponentials and logarithms are inverses of each other. If a logarithm does not have a written base, it's understood to be 10. So base 10 if no base is written. And we also in math call the base 10 log the common log. So you'll hear that frequently as well. Then another special logarithm that you need to know is the base of the natural logarithm, which is that mysterious ln on your calculator. And the base of that logarithm is also not written. It's understood to be e. So in the section where we did some exponential functions, especially with graphing, we had a lot of problems where the base was e. So same thing here, we'll have logarithms with base e. We call those the natural log. So one thing that's going to be important that you know how to do is change between exponential and logarithmic form. This is kind of like just knowing a definition. There really is not a lot of work to show on these. So when it looks like there's a lot of problems, it's because there are many of them where it should take you about 5 to 10 seconds to do. And these are some of those. So this is exponential form, 6 to the negative second power equals 1 over 36. We can see that that's a true statement. So if we're changing, this is exponential, which means that I then want to make it into an equivalent logarithmic form. Because if we are changing, we want it to go to the form it's not in. So logarithmic form is what we want. The kind of script that we use for that is we use the log. Of course, it would be ln if the base were e. But then we put the base of the exponential as the base of the logarithm. We put whatever the answer was as the input of the logarithm. And we set that equal to the exponent. Sorry, my handwriting is really big with this tablet that I use for the screencasting. So for this one, it's not a base e, it's base 6. So I am going to use log. So log base 6, because that's the base of my exponential here. The answer was 1 over 36, so that becomes my input. Typically, when the input is a fraction, we use parentheses. We don't usually do that if it's not a fraction. Then we say equals, and then whatever the exponent was, which in this case was negative 2. And this should also be a true statement. We can check that out in our calculator as well. So let me show you how to do that. So this is kind of my home screen of my emulator here. So if you have an older version, so it's not a TI-84, it's only a TI-83, or even some of the very oldest TI-84s possibly might not have this feature here, but if we go to math, and I always forget which, if it's just in the regular math menu or if it's in one to the side. Yep, there it is. There's something that says log base, and when we get to the additional notes here, we will have some directions for those of you who don't have this, something called the change of base formula. But log base here allows you to just type in whatever you want for the base, and then to type in, let me do alpha y equals fraction 1 over 36. And so you can see we're just going to check exactly what we had, and it does show me, although you can't see it, there we go, that is equal to -2. I'm not saying you have to check them. I told you this is the formula. It is always going to work, but I wanted to prove to you that it does indeed work. So this was the exponential form. This is the equivalent logarithmic equation. So when we are going from logarithmic form to exponential form, the way that we do that is what I like to call the swoop method. And what the swoop method does, that's not an official term, but we start at the base of the logarithm. We swoop around and pick up this 2 as an exponent, and we set it equal to the input. So 3 to the second power equals 9 is the exponential equivalent of that logarithmic statement. And this one, I think you probably believe me. We don't need to do 3 squared in the calculator for you to believe that that is 9. All right, so that's converting between exponential and logarithmic forms. I've shown you both directions. So now in example 2, we are going to do some graphing of logarithms. So a couple of you in the exponential section had trouble with ones that weren't kind of written in that standard form. So I picked one that wasn't written in that form for us to do together here. So really this f of x, if I am looking at my various values, my kind of general form that I'm looking at is y equals a, either log or ln. This is my base. Again, the base is not a transformation. Here's where a c would be, and then we'd have x minus h, and then plus k. The transformations of a, c, h, and k do the same things that they've done in every single section that we've talked about. So I'm not going to re-go through what those 4 do because you have them in your chapter 6 notes from when we did exponentials. So it's going to be the same idea here. So in this case, if I want to rewrite my f of x so that it looks more like this format, I would write it negative natural log of x plus 1 and then plus 2. So in this case, I can see that my a is -1. I also have an h value of -1, and I have a k value of 2. So my parent pattern for a logarithmic equation, so parent, and this I should write general parent. Remember that exponentials and logarithms are inverses. It's the exact same pattern that we had for exponentials, except we flip the inputs and the outputs. So we had -1, 0, 1 for the inputs. Now they're the outputs. -1, 0, 1 for the outputs. Same 1 over b, 1, b for this time the inputs, because one of the properties of inverses is that we switch the input and the output. So in this case, my particular 3 points, because this is a base e logarithm, it'd be 1 over e, so that'd be 0.4, -1. Then I would have 1, 0, and then I'd have e, which is about 2.71. So those are my original points. According to the transformations, a values, I multiply the y coordinates. So I'm going to multiply all my y coordinates by -1. H values, that is a left shift 1, so that means I'm going to subtract 1 from the x coordinates. That's what shifting left does, subtracts from the x. And then k, that's an upshift, so add 2 to the y coordinates after I multiply, of course. So that means that my new points, 0.4 minus 1 is negative 0.6. Negative 1 times negative 1 is positive 1. Plus 2 is 3. Then my next point, 1 minus 1 is 0. 0 times negative 1 is still 0. Plus 2 is 2. And then 2.7 minus 1 gives me 1.7. 1 times negative 1 is negative 1. Plus 2 is positive 1. So these are my 3 points for my transformed graph. So what does it ask me for? It asks me for the domain of my function. It asks me to graph it. Then from the graph, determine the range and any asymptotes. Then it wants me to find F inverse, find the domain and range of F inverse, and graph F inverse. So we've got a lot of work to do. So here's my original graph. So negative 0.6. So here's negative 1. So negative 0.63 would be right here. 0, 2. 1.71. So one of the things that we know about exponential functions is that they have horizontal asymptotes. Logarithms have vertical asymptotes, and your vertical asymptote is always going to be at x equals h. So in this case, I'm going to have a vertical asymptote at, and again, it's part of what I'm asked to do. I'm going to have a vertical asymptote at my h value. My h value is negative 1. So if I draw my vertical asymptote there, that's going to help me to see the shape because I know that my logarithm is not going to cross that asymptote. So here, sorry that my connecting is sloppy, is what my logarithm looks like. Now, let's see, find the domain of f. So I know that you cannot, with a logarithm, have any negative inputs. You can't take the logarithm of a negative number. So that tells me that my domain, in this case, goes from my vertical asymptote to infinity because x plus 1 has to be greater than 0. So my domain is negative 1 to infinity. I already graphed it. Part C asked me for the range and any asymptotes. So the range should be negative infinity to infinity. This is going to keep going down slowly. This obviously shoots up to positive infinity pretty quickly. I also know that because every logarithm is the inverse of an exponential. And we already talked about that the domain of all exponentials is negative infinity to infinity. So therefore, the range of all logarithms is negative infinity to infinity. So that should make sense. I also know, because I already graphed it, that my vertical asymptote is at x equals negative 1. All right, so then part D is to find the actual F inverse. So I'm going to do that in a different color here. So part D, find the inverse. So step 1 is to put y in place of f of x. Next step is to switch the x and the y. Sorry, sometimes it's hard to use this tablet and it gets to be a little much. So then, because we want to get y alone here, we're going to need to move everything so it's just a single logarithm over there, because we know we can get rid of logarithms using the swoop method that we did in example 1. So I'm going to subtract the 2 on both sides. So that gives me x minus 2 equals the opposite of the natural log of y plus 1. So then divide by -1 on both sides. So then that's going to give me either 2 minus x or negative x plus 2, whichever way you want to write it. It doesn't really matter. And so now, in order to get rid of the logarithm, I need to use the swoop method. So remember, since this is natural log, that means the understood base is e. So you don't have to write it. I'm just writing it to illustrate the swoop method. We start at the base. Notice that this time, it's like mirror imaged. My base was on the left side here, and I swooped around to the right. So here, my base is on the right side, so I'm going to swoop around to the left. It goes this way, the swoop does. So it's e to the 2 minus x power equals y plus 1. So then I would subtract 1 from both sides. That's going to get y alone, which means that that's my inverse. So f inverse of x equals e to the 2 minus x, or negative x plus 2, if you prefer. Or even better yet, we could do negative x minus 2. So pretend that that's a minus there. And then I've got the -1 on the outside. So the reason why I said even better yet is because then this is like in the CHK format if I factor the -1 out, because then I can see I've got a right shift, and then I've also got the reflection over the y-axis. So for my exponential here, I know that I'm going to be multiplying the x's by -1. I also see that I'm going to have a right shift there, and I'm going to subtract 1 from the y coordinates. So if I go to make a table of values, so -1, 1 over e, which, again, I'm starting with the reverse of these. So here's this guy, then starting with 0, 1, and then finally the third point would be 1, 2.7. So again, these transformations tell me to multiply the x's by -1. And they also tell me to add 2 to those coordinates. So x coordinates, add 2, add 2. And then this -1 on the end, subtract from the y coordinates, which means that the transformed -1 times -1 is +1 plus 2 is 3. So I'm just going to write it as a table. So 3. And then 0.4 minus 1 is -0.6. And then 0 plus 2 is 2. 1 times -1 is -1. or 1 minus 1, it's not multiplication, it's subtraction. 1 minus 1 is 0. And then for the last one, this gives me -1 plus 2, so that gives me 1. 2.7 minus 1 is 1.7. Now I did it the transformations way because I wanted to prove to you that the properties of inverses should hold true. Now, do you need to graph it with transformations every single time? Absolutely not. Now, I had to find f inverse of x. The directions asked me to. But I could have graphed it by simply switching the x and y coordinates of my original to get my inverse. But here I did it with the transformations to prove to you that it works. So again, unless it says you have to use the transformations, you don't have to do that. So 3 negative 0.6 would be right here. 2, 0 would be right here. And 1.7 would be right here. I know that this is an exponential, so y equals -1 is going to be my horizontal asymptote. Logarithms have vertical asymptotes. Exponentials have horizontal. So I'm so sorry that the connecting of the dots is so bad there. Really tried hard. And we can tell that they are indeed reflections over the line y equals x. So I have pretty much run out of room, but the only thing left is the domain and range of f inverse. So that's good. I don't have a lot left to do anyway. So the domain is going to be the range of the original. So -infinity to infinity, which makes sense because that should be the domain for an exponential. The range goes from the asymptote up in this case. So -1 to infinity, which is indeed the domain of the original. So again, domain and range are flipped. This all makes sense. Everything that we've learned about exponentials is holding true here. So, last thing we need to talk about is how to solve some logarithmic equations as well as some different kinds of exponentials. So, on these types, the first thing we're going to do is to isolate the log or the power, depending on whether it's a logarithmic or an exponential equation. Then we will solve by using inverses or making bases match or the swoop method. Step 3 is going to check for extraneous solutions on logarithmic equations. So always check for extraneous solutions on log equations only. You don't have to check for them on exponentials. Because again, remember, you can't have the input of a logarithm be negative. So if your input is negative, then you have to throw out that solution. So when I look at step 1, isolate the log. All I have is a log on the left side. It's got the log, it's got the base, it's got the input. That's a single logarithm. So that means that I can convert it to the exponential form by using the swoop method. So I can write 3 to the second power equals 4x minus 7. 3 to the second power is, of course, 9. So now it's a simple linear equation to solve. So add 7 to both sides, then divide by 4, and I get x equals 4. It's a logarithmic equation, so I do need to check my solution. 4 times 4 is 16. 16 minus 7 gives me 9, which is not a negative number, so it's okay. X equals 4 is a valid solution. On part B, it is also just a single logarithm on the left side. So that means, again, I can use the swoop method. Now this time, there's multiple terms on the right side. That actually doesn't change what I do. It just changes the fact that the exponent has multiple terms there. So swoop 6 to the 5x plus 3 equals 36. So then, just like we did in the previous sections, I'm going to make the bases match because my variable was in the exponent. And so if I rewrite 36 as a power of 6, if the bases match, that means that I can drop the bases and set the exponents equal. So that gives me 5x equals -1, or x equals -1/5. So then I need to see my logarithm input, the value here is already a number. So no matter what x is, it's not going to make the input of my logarithm negative. So this is a valid solution. We are good with it. All right, last one. This one I do have to do step 1 because this power is not isolated. It's got that multiplied 4 in front. So my first step needs to be to divide both sides by 4. So e to the x plus 1 equals 5/4. So here's where I run into an issue because I cannot write 5/4 as a power of e. So when you can't make the bases match, we use the logarithm on both sides because a logarithm is the inverse of an exponential, which means I can undo this base e exponential if I take a base e logarithm on both sides. So the logarithm with base e is the natural log. So I am going to natural log both sides. Again, I'm doing that because the natural log is the inverse of the exponential with base e. So what ends up happening is that these cancel each other out. So I just end up with x plus 1 equals the natural log of 5/4. And then to get x alone, I would just subtract 1 on both sides. So x equals natural log of 5/4 minus 1. Now, this is not a logarithmic equation, it was exponential, so I don't have to check for extraneous solutions here. You also, unless it specifically tells you to round, that means it wants an exact answer, so you do need to leave it with the log in the answer unless it tells you to round it. All right, I think that should hopefully set you up well for your practice.